Hey guys, this is Professor Janacek. I want to go over some examples where we take derivatives of exponential and logarithmic functions. Now, our rules for exponential functions, if we take d dx of b to the x, we get b to the x times the natural log of b. And the other rule for logarithmic functions, if we have d dx of the log base b of x, that's equal to 1 over x times the natural log of b. Now, I'm not going to prove these rules, but it is, of course, based on the limit of the difference quotient. Also, notice that these are going to work for any base, whether we have a base of 10 or of e or of b. Our most common base, of course, is e in this situation. So you might actually remember this as if I take the derivative of e to the x, notice that is e to the x times the natural log of e, but the natural log of e, this bit here, that's just 1, so we end up with e to the x. Looking at the logarithmic function that has a base e, remember that's the natural log. So if I'm taking the derivative of the natural log of x, I get 1 over x times the natural log of my base. Remember, the base here is e. And again, the natural log of e is 1, so we get 1 over x. And we use these two rules quite often. Let's try some examples now. We want to determine the derivative. Example 1 here, we have y is equal to the natural log of 4x. So dy dx would be, well, this is a natural log, so again, with the natural log, I could actually just use this version of it. It's simply 1 over x, but of course, in this case, we don't have just an x, we have a 4x, so it's 1 over 4x. And the chain rule now says I have to take the derivative of that inside bit. So the derivative of, again, the inside here is 4x. The derivative of 4x is 4. So we have 1 over 4x times 4. The 4's reduce, and notice we end up with just 1 over x. Pretty nice. Example 2 here, we have y is equal to x times the natural log of x. If we want to take the derivative of that, notice it's a product. So we're going to have to use our product rule. X is our first, and natural log of x is our second function. All right, so we take the derivative of the first, which is 1, times the second, plus the first times the derivative of the second, and the derivative of the natural log of x is 1 over x. We can simplify this. 1 times the natural log of x is just the natural log of x, plus x over 1 over x, that's just 1. So we end up with the natural log of x plus 1. All right, on to example 3. We've got y is equal to the natural log of the absolute value of the secant of x. So to find the derivative of this, the derivative of the natural log is simply 1 over that argument, so 1 over the secant of x. But again, chain rule says we need to take the derivative of that argument as well. The derivative of the secant is secant of x times tangent of x. Of course, we can reduce those secants, and we end up with just the tangent. Okay, check this out. Make sure you understand what all happened. I took the natural log of the secant of x, finding its derivative, we get just the tangent. Isn't that nice? That could be a helpful thing to remember. The derivative of the natural log of secant of x is simply the tangent of x. On to example 4 here, we have y is equal to the natural log of x squared over x squared. So, to find the derivative of this, looks like in this case, we're going to have to use the quotient rule. I've got a function in the numerator, the natural log of x squared, and a function in the denominator that has an x, that's x squared. So, quotient rule for this one. The quotient rule says we're going to start with the derivative of the numerator. So my numerator, the natural log of x squared, its derivative is 1 over x squared, but chain rule says I have to take the derivative of x squared as well, so we get 2x. So that's all that right there is just the derivative of the first, of the numerator. We're going to multiply this by the denominator, and then minus the numerator, natural log of x squared, times the derivative of the denominator. And then all of this is being divided by the denominator squared. All right, let me clean that up a bit. Let's see, we can simplify all of this quite a bit. In the numerator, this first term, this x squared and that x squared, those reduce. So we get 2x minus, in this second bit, we have 2x natural log of x squared. Nothing can reduce here. Actually, let me... And then, of course, this is all over x to the fourth. One other thing that I notice I can do is I can take this exponent and multiply it there in the front as a coefficient. That is one of our properties of logarithms, so we get 2x minus 4x times the natural log of x squared. Oh, not x squared, just x over x to the fourth. Now, since all of these have an x, I have an x in the coefficient of all of those, I'm going to go ahead and factor that out so we can reduce it with one of the x's in the denominator. So we have x times 2 minus 4 natural log of x over x to the fourth. Reduce one of those x's, that gives us 2 minus 4 natural log of x over x cubed. And there we go. Yes, there are a few other things you could possibly do with this. Move that 4 back to the exponent, but this is perfectly fine. All right, moving on to example 5 now. If we have f of x is equal to 3 to the x, here's an exponential function. So what is f prime? Well, according to our rule there at the top of the page, it's just 3 to the x times the natural log of 3. And that's pretty much it. It is sometimes common to write that natural log of 3 as the coefficient. So natural log of 3, remember that's just a number, times 3 to the x. Either way, it's completely acceptable. All right, on to example 6. G of t is equal to 108 times 2 raised to the t over 12. So to find g prime of t, notice our variable here is t, we're going to keep that 108 and then simply take the derivative d dt of 2 to the t over 12. So keep that 108, and then we'll multiply by, so again, this is the exponential rule. I write that exponential as is, and then we take the derivative, and then we multiply by the natural log of our base. But then this one, we also have to take the derivative. This is the chain rule. We have to take the derivative of that exponent. That exponent, t over 12, the derivative of that, gives us 1/12. Now we can reduce the 108 with the 12. So it looks like, oh, and I need a parenthesis on this, looks like we end up with 108 over 12 reduces to just 9. We still have the natural log of 2 there. And then, again, that's my constant, so I move all of that to a coefficient, and then multiplied times 2 raised to the t over 12. All right, there we go. Lots of numbers there. Notice not too many t's, not too many variables, but lots of constants and coefficients. All right, on to example 7 now. Y is equal to x raised to the pi. All right, this one is kind of tricky. It's here on this page of exponential and logarithmic functions. However, notice where the x is. X is not in the exponent. X is here as part of my base. So this is not exponential. My exponent is not, my variable is not in the exponent. So it's not exponential. So in this case, we simply need to use the power rule. I don't need to use that exponential rule. So the power rule says you simply take that exponent, write it as the coefficient, and subtract 1 from the exponent. Oh, there we go. Actually, this probably be more appropriate. All right, and there we go. That's all there is to that one. Again, we're using the power rule, not our exponential rule. Now, example 8 looks very similar. We've got y is equal to pi raised to the x. Now, in this case, my variable is in the exponent, so this one is an exponential. So we'll use our exponential rule, which says we get whatever our base is raised to the x, that exponent as is, times the natural log of that base. And again, sometimes it is rather common to put that natural log of pi. That's just a number. It's a constant. I'll move it to the coefficient spot. And then times pi to the x. There's our exponential. Either way is good. All right, on to example 9 here. Don't need that there just yet. So we've got y is equal to x squared plus 4 raised to the e. Again, be careful with this. I have an exponent in here. Yes, there is that e as an exponent, but notice where my variable is. X is in the base. Again, this one is not exponential. Even though it tricks us by putting an e up there in the exponent, it's not technically an exponential. E is just a number. 4 is a number. 2 is a number. Anything that's in an exponent is not the variable. The variable is just in the base. So to find the derivative of this, we simply need to use our power rule. And of course, in this case, we'll use the chain rule as well. So our power rule says we'll take e times x squared plus 4 raised to the e minus 1. And now the chain rule says we're going to take the derivative of the inside. That inside, x squared plus 4, the derivative is 2x. We can simplify this just a little bit. Actually, not much. I'll just turn things around a little and write that coefficient 2x e, and then x squared plus 4 raised to the e minus 1. All right, so there we go on that one. Again, not an exponential, trying to trick us here. Example 10, we're back to a logarithm. F of x is equal to log base 3 of 2x plus 1. So our log rule, if you remember what that looks like, we'll write this as 1 over our argument, 2x plus 1. And then here in the denominator, we're going to multiply by the natural log of our base, so that's the natural log of 3. Now the chain rule says we also need to take the derivative of that inside bit. The inside bit here is 2x plus 1. The derivative of that is simply 2. We can simplify this just a bit. Oh, not 2x, just 2 as I said. So we can simply rewrite this as 2 over the natural log of 3 times 2x plus 1. All right, not a lot going on that one, but it does seem to be a little confusing, so take your time with it. Here we don't have a base of e, we have a base of 3, and then of course we have to use the chain rule, and multiply by the derivative of that inside function on the composition. All right, finally, example 11 here, we have t of n is equal to n log base 2 of n. Notice my variable here is n, but I do have two of them, one here and one there, and it looks like there is multiplication going on between those, so we will use our product rule. So t prime of n, we will start with the derivative of the first. The first piece is just n, so the derivative of that is 1, times the second, log base 2 of n, plus the first, which is just n, times the derivative of the second. The second here is log base 2 of n. The derivative of that, I have to use that log rule, that's 1 over n times the natural log of the base, which is 2. Looks like we can simplify this a bit. We've got log base 2 of n plus, notice here, these two n's reduce, one in the numerator, one in the denominator. So we end up with just 1 over the natural log of 2. Now, there is a result, but I think we can clean this up just a little bit. It'd be really nice if I could combine those two fractions and get a common denominator, which would be the natural log of 2. Now, I can rewrite this using our change of base formula for logarithms. Remember that change of base formula says I can rewrite this using a natural log. It's the natural log of my argument n over the natural log of my base 2. So now we've changed to the base of 2. And now I see I can combine those. So we get natural log of n plus 1 over the natural log of 2. And there you go. Enjoy!